Good evening, everyone. Welcome to a brief introduction of microsensors, week one, the live interactive session. The course instructor for this course is Professor Santanu Talukdar from ISI Bhopal, and I am the PMR of Teaching Assistant Vikas Pandey from IIT Jodhpur. So, this is a brief about me. I am a PhD scholar in space science and technology at IIT Jodhpur. I have an academic background in VLSI and electronics and communication. I've worked as R&D engineer, digital fabrication engineer, and robotics trainer before starting my PhD. I work in area of HEMT, sensors and IoT and microfabrication. The class, this live interactive classes will be will be on Saturday 3 p.m. The meet link will remain same. That is what you have joined today. And all the recording of these classes will also be available over YouTube channel. And in case you need to contact me or find more details about me, you can go to my portfolio and or you can mail me in case you need some help. So before we delve into this topic of week one, if you have any questions, you are free to ask. And during the class, I will not be able to check the messages. So please feel free to unmute yourself and speak up. Yes, any questions or any queries? And this is an interactive session. So the best thing is that you have to ask. If you ask, that will be the best thing. So before we start, I would like to know a bit about you all. If one by one you people can pick up. Yeah, Karuppa Swami. Yeah, can you introduce yourself? Like, what is your background? And why you are here in this? Like, why you are interested in this subject?
Uh,
Yeah,
Good afternoon, sir. I am Karup
good.
Sami.
Yeah,
Uh, I am now working at PAG Institute of Technology, uh, lab instructor.
okay.
I'm I'm completing VLSI design in uh, Allaman Engineering College. Uh, um, this course interested to my research purpose.
Okay, okay, great.
Okay.
Yes, anyone else would like to introduce?
Yes, sir. I'm Sudhakaran.
Yeah,
I'm studying third year electrical and electronic communication engineer.
okay, great.
I
And
have interested to know about the microsensor, sir.
yeah, anyone? Yeah, Sam Thomas, can you introduce? I think there are some participants who have joined as viewers. I don't know. Like, is, is there an option that you, while joining, you are joining as viewer or something? Because I think this is a new option which has come. Earlier, it was not there, right? Yeah, Ashwin, yes. Any, you would like to ask something? Yes, hello. Ashwin Roch, are you there?
Sir, can you
Yeah,
hear
yeah.
me?
Hello. Yeah, anyone else can introduce? I think Blessing CA. Yeah, yeah. Please speak up about you. Like, what is your academic background or what you are presently working
Sir,
I am a first year EC student studying in St. Joseph's College of Engineering
Okay,
in Chennai.
great.
I
Okay,
would like to know more thing about sensors and in my department.
great. Okay, so what I
Thank you, sir.
conclude is mostly most of you are like somewhat related to electronics or EC. Okay, fine. So let's move with the topic. So any questions related to week one, what has been covered by sir? If you have any queries or something you are not able to understand, you can ask at the beginning or even after we complete this. Like we are able to, like once we are completing this summary, then also you can ask. So any questions for now? Anyone? Okay. So let's start with our uh, class. So we'll start with MEMS. So anyone knows what is MEMS? Uh, I think you have like seen the first week of the lecture. Yes. Anyone can say what is a MEMS? Yes. Please speak up.
Sir,
Don't
is it a
shy.
medical sensor?
Okay. Yes. Any other view on this?
Sir, micro electromechanical systems.
Great. Micro electromechanical systems. Okay. So from the word itself, we can see there are actually three things in this which we have to understand. One is micro, second one is electro, and third one is mechanical. Okay. So micro. Uh, eh, can anyone say what is like what do we mean by micro? Yes. Please speak up.
Sir, a small or minimal compartment.
Great. Good. Any other answers? Yes.
Sir, things which are in a dimension of 10 to 10 power minus 6.
10 to the power minus 6. What? Kilogram or what? We are talking in terms of dimensions. So length, right? 10 to the power minus 6 meters. Or we can say when we are talking something, ideally any object have three dimensions, right? Do you agree that we have length, breadth, and height? If at least one of these dimensions is in the range of micrometer, that is 1 micrometer is equal to 10 to the power minus 6 meter, right? So even if one of these dimensions is in micrometers, it is considered a micro micro device. Okay, like when we are going further in nanotechnology and all, so there we are saying that at least one dimension should be in nanometer range. So similar to that, uh, when we are talking about devices which have at least one dimension in micrometer range, so they might have a thickness in micrometer range or length in micrometer range or width, length, width or height in micrometer range or all three of them in micrometer range. Such devices will be part of MEMS. Then second thing is electro. Okay, so can anyone talk about this? What this must be meaning? Yes, anyone? Okay, so
It's work by the electrical system, sir.
yes, electrical system where electron flow plays a role in the working of the device. And then the third component is mechanical. That means there are physical moving parts. So a system that has dimensions in the range of micrometers have electrical as well as mechanical systems are considered the part of MEMS systems or micro electromechanical systems. So they, or we can define it as integration of electrical and mechanical components at the micro scale level. So why we are interested in this? Because there is a huge application of these systems. In fact, we are commonly using in our day-to-day life, and we are not able, we might not be understanding that actually it is a MEMS device, but we are very commonly using it. Like if you see, this is a MEMS microphone. Nowadays, very good quality microphones, they are MEMS devices. Then if you see this one, now can anyone guess what is this? So tiny thing. Yeah. Yes, anyone?
Sir, some type of chip used for this material.
Yes. Any other guesses? So you people know about this. This is called as diabetes, right? It's very common, right? So when it goes into extreme levels, people used to get insulin injections, right? So this small device is a MEMS device that is used to deliver insulin without pricking and can just be like you see, it can be attached to the body and the device will deliver like will deliver the insulin in amount as required by the body. So it makes it much uh, comfortable and easier also. So such as well as most of your phones have nowadays gyroscope and accelerometers. Like when we say that we are navigating somewhere, we are going to some place via navigating through Google Maps or any other maps, we are able to see which direction we are going. That is due to accelerometer and gyroscopes inbuilt into our phone. That is again a MEMS device. So what is the advantage is that if we compare it with a compass that was used traditionally, that used to be big, bulky, in fact weighing almost equal to our phones. So the first thing is like it has been miniaturized. That means it is lightweight, has high functionality. Like in the same mobile system, we see a lot of systems are being built because they are smaller. What if we had a big compass, big accelerometer, and everything? It would not have been convenient and easy to integrate in one system. Just like that, many MEMS systems are helping to miniaturize big systems that used to exist. Okay, they have higher functionality due to like working in smaller scale. We are able to get a lot of systems inbuilt into smaller area. And the third thing advantage is its integration with electronic systems. Fine. Any questions still here? Any doubts you have? Anyone?
Sir, please could you more tell about the integration with the electronic?
Integration with the electronics. See, when we talk about mechanical systems, okay, Traditionally, mechanical systems were mostly like uh, they were independent. They didn't have electronic system like they didn't have display. The output used to be somewhat like mechanical work or like suppose you have a pulley system or what you say like we will see a cantilever system where something is oscillating or something is moving. That conversion to electrical signal at a large scale. Suppose that you have a pillar, a, a hanging cantilever, pillar or cantilever, you can say, and it is vibrating. And this vibration is due to the force that is being put upon it. So, to convert this force into a corresponding electrical signal or to measure it easily, it was not that easy. But when we get into MEMS system, the same thing becomes much easier. Like we can coat a very thin film of, say, some piezoelectric material, which changes its electrical resistance based on stress and strain, and we are able to get our electrical signal. Got it? Like that makes it easier. Yes, yes, Sudhakar. You were saying something?
Thanks, sir. It is easy to understand.
Now, okay, okay. As we go forward, you will see some more things which will make it even easier to understand this concept. Any other questions here? Anything? Okay. So first thing is that why to scale device? Like why we are making devices smaller? Why bigger is not better? Okay. So as I said, smaller enables better performance and energy efficiency. We can do the same task with using lower energy. That means to run the same device, we will need a lower energy and we will get better performance in the sense that suppose that we have to like since most of you are from electronics background, so we can say that let's say we used to have a normal resistor, carbon resistor, right? So when using in bigger circuit, it's fine. It is this small, but the propagation delay, you can say, like delay between this is in say milliseconds, 1 or 2 milliseconds. One device is fine, one resistance is fine, but what if our circuit uses such 200, 300, 500, or say 1000 such resistors? So the cumulative delay will be too much, say 1 to 3 seconds. Now you see, when we are talking at present, my sound is going through like my sound is going through earphone, then going to my device, then getting transmitted to you, and my like my video is going through the camera that is a separate device and going to the internet. So if there is a mismatch between my voice and the camera, like there is a delay because some additional system is there, it will actually cause some glitch. It will not be that smooth. Whereas if we have miniaturized system, like in lower, like smaller systems, this delays are in say nanoseconds. Okay, so overall delay that may be in 10, 20 microseconds or milliseconds, you will not be able to notice any appreciable difference. That enables better performance, as well as we are able to work at a lower energy. We are using lower voltage nowadays compared to what we used to have, like say 10, 20 years ago. All our devices used to be working in full DC 220 volt. Nowadays we see most of our devices are working at 5 volt DC. In electronics also, we used to work earlier at 12 volt. Now we are gradually moving towards 3.3, then 2.3 and 0.3 like that. Then there are some surface forces like capillary action, adhesion, and surface tension that are not relevant at macro scale. That means when we are talking about bigger scales like millimeter range, these things might not play big role. But we can use these forces like capillary action, adhesion, and surface tension in uh, micro scale, not in macro scale, or like you can say millimeter range and this or meter range. These are not that relevant. Like if you see uh, some insects, this is actually water walking insect. Okay, so it can walk over water because it uses the surface tension that is provided by the water over its leg. It has very thin hairline features that enable it to walk over water. So such thing, like that is an example from the environment, naturally occurring use of a micro device. So such features can be incorporated into our electromechanical devices. So if we do a comparison between macro scale forces and micro scale forces, okay, so what is the difference when we talk about our day to day, what is visible to us, what forces do play a role here, and what forces do play a role when we go into micro sensors or micro device or MEMS. Okay, so the first difference is the dominant forces. Okay, in case of our macro devices, we have gravity and inertial forces or Newtonian forces coming into play very commonly. Whereas when we talk about microscale forces, adhesion, capillarity, and van der Waals forces are more dominant there. Like gravity and inertial forces, these are not that relevant when we compare with the amount of force like adhesion, capillarity, and van der Waals. So gravity, like you see in our case, it dominates like macro scale forces. It dominates overall behavior. But when we are talking about micro level, it is negligible due to low mass. Since we know that gravity is equal to G m1 m2 1 r square, right? I'm not sure. F was it? F is equal to some constant was there, right? So here mass is relevant, but in case of this micro devices, the mass will be very small, and so gravity will almost be negligible. Then a very important thing is surface to volume ratio. We are able to utilize this feature that when we shrink devices or scale devices or anything, when it gets smaller and smaller, the surface area compared to the volume of the device or structure increases, and that facilitates a lot of active sites for our uh, let's say reaction or anything. If you recall what you might have studied in your intermediates like 11 12s and all, you must be have heard about like when we talk in chemistry, somewhere it is written finely divided palladium is used as catalyst. Anyone remembers for like hydrogenation and all? At many a place it is written finely divided palladium, finely divided platinum, like that. Anyone remembers? Okay, so now if you if you check that, you will find that even traditionally it has been used that to increase the surface area. Say we want to have more reaction sites, over our say some material, like we are using a catalyst, so we want that all the reaction elements should be like there should be ample space for them to bind to the surface. In that case also, the size is reduced. Reducing the size will actually increase the surface to volume ratio. So for the same volume of the same volume of the material, we will have a larger surface area because it is finely divided or in smaller particles. Then at macro scale, friction is proportional to the weight, whereas in case of micro scale devices, it is proportional to the surface contact area. So again, mass or weight doesn't play much role here. In case of if we talk about energy dissipation, there are also bulk material properties like mass and other factors will play a role. Whereas in case of microscale, surface phenomenon and damping will play a role. When we talk about big devices, uh, like not device, I can say big macro scale things. If we are reducing the size, say like something is of 1 kg, a mass of 1 kg, we are replacing it with 2 kg. The effect of say force over it and effect of gravity friction will proportionately increase or decrease. But this is not the same when we are talking about micro scale forces, because there surface area doesn't like surface to volume ratio actually increases many folds when we are reducing the size, and that's why this the force effect increases or decreases very non-linearly, not exactly in the terms of reducing the size. And that's why reducing a bit, like just halving the size, might bring a lot more advantage to us. And specifically nowadays, like when people are moving from micro to nano, this role even increases further. So surface texture in case of our macro scale forces it has minimal effect, whereas in case of micro scale devices it has a lot of effect. And that is why when we are making sensors or chip, smoothness, what is the roughness, uh, even this nanometer variation in roughness will have dominant effect over your devices. In case of thermal conductivity, again bulk conductivity will be there, and in case of microscale devices, again it will be through surface interaction. So uh, since there is not enough you can say enough bulk for this thermal conductivity or other things to happen through the bulk, so it is thin enough that it is like the surface itself, it is almost equal to the thickness of the surface that we talk in case of bulk devices. Fluid flow, like this is very crucial in case of MEMS devices, because there is like a separate section inside MEMS devices which is microfluidics. Okay, so if we think about something that if a fluid is flowing, like if we have this fluid over this, if we tilt it in our macro devices, since it is having inertia, and like inertia and these things will come in play, some force will, so it will flow like this. But when we are talking about microfluidics or micro devices, it is very much laminar, and inertia and this gravity, these roles get out of like these forces are not dominant and will not affect our devices much. So some examples of macro scale forces like car, building, planes, this. Okay. In case of micro scale, there are MEMS devices, microfluidic devices, lab on a chip device. That means a single chip kind of chip in which a lot of processing is happening. Like one of my professor, he worked towards making a device which takes in the blood, blood of the patient, just one to two drops. That is even more, and the whole that chip itself, it will just flow. It will separate WBC, RBC, everything in that small area only, and then it will it will count how many, like how much RBC and WBC is there in the blood, and it will be able to show it or read it out. Okay, so such devices are called lab on a chip. So the work of a lab technician is all carried out in a single chip. So any questions or any doubts still here? Anything someone would like to ask? Please unmute yourself and speak up. Yes, anyone? I am audible to everyone?
No question, sir.
Okay. And anyone else? No? I cannot see the messages. Please speak up. This is an interaction session, not a messaging session. Please. Yes, I think someone has messaged. Yeah, Karupa Sami. You have, you can unmute and speak up. Okay. So let's move to our next slide. So as we were talking about scaling laws, okay, the surface area scales with L square since it is length squared, while volume scales as L cube. That means reducing the, like, if this is a cube, say all 2 micrometer, all the sides. So if you calculate its surface area and its volume, and then if you just half the sides, like all L from 2 micrometer to 1 micrometer, you will see the volume changes much more compared to the surface area change, and that's why the volume to surface area to volume ratio increases. So surface area is higher in smaller device, like smaller sizes compared to the volume. Okay, so if we talk about a cantilever, this is a cantilever, that is a hanging pillar kind of structure. This one, this is you see this device, the scale is, this is taken from a paper published by University of Edinburgh. Okay, so this is the scale is 10 micrometers, so we can say that this length is almost about 20 micrometers, 20 to 25 micrometers. Okay, so if and this is like the platform. If the same thing we are trying to build in case of some building, uh, a civil engineer goes to build a proportionate thing in real world, it is quite difficult to support such large protruding structure or pillar because its weight will be too much compared to what the force will be able to handle. But when we talk about micro cantilever or micro scale devices, so the strength, like other equations are still in play, like what will be the force and all those things. But since the weight has reduced a lot, this will be fine and it will be firmly hold. it will not have the problem of getting disturbed, like it will not break easily, just like if we see in a like macro scale or a big building. If such a structure is made, everyone will go and, like, whenever someone passes, they will see this will fall soon. But the same thing if it is in a micro scale devices, like these are real devices, cantilever devices, which are successfully made and they work for a lot of time, like years together, and they work perfectly. Okay, so they retain the proportional strength with significantly less weight and thus are able to sustain for a longer time. So if we see about these cantilevers, okay, yeah, any questions still here? Okay, so if we talk about this cantilever, there is one application, that is AFM. Anyone knows about AFM? Anyone here who knows about AFM? Atomic force microscopy. Yes. Anyone? Okay. Yes.
The photo,
Yeah.
the photo diode using and laser light use பண்ணி அது I'm not clear how.
Yeah. No, I am asking that if anyone, like, do you know about AFM? What is a AFM, or what a AFM is used for? Yes. Anyone? Anyone else? Uh, yeah, Dr. Madik. Hello, are you there? May I ask someone? Yeah, Sam Thomas, are you there? Hello. Yeah, Sam, are you there?
Yes, sir.
Are you getting what is, like, what is going on till here?
Yes, sir.
Okay. So have you ever used a microscope, or are you familiar with microscope?
Yes, sir. I have used during my school time, during
Okay.
practical exam.
Yeah. So at least microscope, I can assume everyone knows. But what if we want to get into very smaller details? Say microscope has a limit, and some of you might be aware about the Rayleigh criteria and all that. We will anyway be covering when we talk a bit about lithography and all. Okay, so light have a limit. Light, what resolution it can give, it has a limit. It cannot go beyond that. It cannot go into much finer details. Like we cannot see atoms. We cannot see like very fine roughness. What we might be considering as a very smooth surface, if we see a very like if we get a very closer look of it, we will see that actually it have some nano and micro scale um, deformations. Okay, so such things we can see using some specialized techniques like SEM, FESEM, and to understand the surface roughness, we use a technique called AFM, atomic force microscopy, and it uses the MEMS cantilever for this purpose. And what it has is that it will have this hanging pillar kind of structure, the cantilever, and it will have a tip, and this tip will uh, move over the surface of the material or surface of the film or whatever surface we want. It will move slightly on the surface of it, and due to the roughness of the surface, certainly this roughness cannot be very big, it should be in micro and nano scale. So this will move like up down, and we will continuously be putting a laser over it, and it will get deflected, and this reflected, and this reflected beam will change according to the like height or depth of the surface, and that will be detected by the photo detector, and as such the surface texture of a film can be obtained. For this cantilever, MEMS cantilever are used. I think I have one. Okay. I think I kept it somewhere. I have like I could have shown you some in some classes. I will show you that what this cantilever looks like. It is very thin, like you cannot see the tip and all. Okay, you cannot see the tip and yeah. Someone is messaging. Yeah, I have said at the beginning only. Please speak up instead of messaging. Yes, anyone? Karup Karupasamy. Yes, you have to say something. Hello.
Sir, the copy from AFM same type of microscope, yes.
Uh, Not exactly the same, but similar, you can say. Scanning probe microscopy and
Okay.
AFM are similar. Like the concept is very much similar, you can say. Okay.
Okay, okay, sir.
Yeah. Please,
Okay, sir.
you can freely interrupt me. Anyone can freely interrupt me. They can ask questions because this is not a conventional class. We are supposed to be interacting more and discussing what already sir has done. If you go to the lecture, you will see that most of these things are like discussed in much more details than what we will be discussing here. So you are free to uh,
First time interaction section, so little bit fearness.
no, not an issue. Like please feel free to ask because this the whole purpose is to have questions from you and have an interaction. It is not meant to be a one-sided like lecture. Okay, so such uh, such MEMS devices, the cantilever, like so, how they deflect, like how the deflection of this cantilever will occur up down. Like there will be two forces in play: axial force and transverse force. Okay, so can anyone explain what will be what is like meant by axial and what is transverse? Anyone? No. So any structure will have like when it is moving or it is vibrating or if it is you say it is oscillating, in that case it will have two set of forces over it. That one is axial, that will try to like move it in right left direction, and one is transverse, that will try to move it up and down. So these two forces are defined by the equation EWH upon L to delta L, that will define the axial force, and transverse force 3EI upon L cube to W tip. So E here is the Young modulus of the material, the cantilever material. W is the width of the structure. So whatever is the, if we see on the top, actually it should be a bit thicker, so it will have width. H is the height, that is the thickness, we can say here. Okay. L is the length of the structure, the hanging structure, and delta L, that is when it will move left to right, what is the change in the length delta L due to the strength, that is delta L. That will give the force that is over it. If we talk about the transverse force, here E is Young modulus like earlier. I is the area moment of inertia. Okay, so this depends on the cross section. This I depends on the cross section of the shape of beam. Okay, so typically it is like for a rectangular beam, it is W, like what do you say, W H cube by like half of WH cube, something like that. Okay, width by yeah. So L is the length of the beam, and W tip is the deflection at the sorry, deflection at the tip of the beam, like not this one. Here, what will be the deflection? That will be the deflection, that is the same deflection that will occur here will actually occur at the bottom. Okay, so this is the equation. We will not delve too much deep into equation and derivations. We are just saying that what are the significant things. We will mostly, like in this week, it has mostly been discussed about what is MEMS device, what is its significance, why it is being used, and then we will see how some MEMS device and MEMS sensors are actually fabricated. Okay, so we will be delving into that part. So how, since a system is having some stress, strain, and these things, so it will certainly have some energy stored in due to the deformation, and that energy is given by half sigma epsilon into V, where sigma is, yes, anyone knows what is sigma, what is epsilon here? Yes, yes, anyone? Some of you have seen the week 1 lecture of sir, anyone? Yes, yeah, Dharmi, you have some question? Hello, hello, Dharmi, are you there?
So sigma represents some kind of a force or a acceleration.
Okay, sigma is the stress and epsilon is the strain. And stress, we know sigma equals to force upon area, and epsilon, that is the strain, that is equals to delta L upon L. Okay, and V here is the volume. Okay, volume of the material in meter cubes. Okay, and half we know that this is a constant 1 by 2. Okay. So there is a related Castigliano's theorem that helps us derive deflection or force from the strain energy, and from that we get here. So this whole thing is used to analyze MEMS resonator and oscillator. So one application I have shown you, AFM, and MEMS cantilever has a lot more application like MEMS resonator, specifically when we need to know the frequency, like say like microphones and all, like they will resonate at a specific frequency, and once that matches and all, so MEMS resonators are used, MEMS oscillators are used. Okay, so this is the like one example we can see of MEMS. But how such devices are fabricated, how these devices are made, if we talk about MEMS or micro sensors, let's say micro sensors for simplicity. Okay, micro scale sensors, right? So yeah, anything till here? Any questions, anyone? Anyone? Am I audible? Okay, so this is like, now we are starting our main topic, that how these things are made, how they are fabricated. So there are some core processes that comes from, we can say, chip, uh, chip when we talk about semiconductor chip, that the process has been optimized in semiconductor fabrication facilities, semiconductor fabrication, and similar processes we use in case of MEMS devices also. So things like lithography, etching, deposition, and doping. These are some of the core processes that are used in case of fabrication. Just like using the same technology, we adapt it for microsensors. Okay, so one of the most important processes is lithography. Anyone knows here about lithography? Yes, please. Don't be shy. I am not asking questions to judge. I want to know that what you know, so that according to that we can discuss things. So please speak up. Yes, anyone knows about lithography?
No, sir.
Yes,
No, sir.
no? Okay. Yeah, anyone, like any other processes that we have talked about, lithography, etching, doping, at least I think some of you might be aware of
Yeah, doping, sir.
doping. So what is doping?
Adding impurities to
Yeah,
a
adding
pure conductor.
impurities to, yeah, good, to increase its conductivity or tune its conductivity. Great. Okay. So lithography is, yeah, when we will do lithography, we will see lithography. We'll see in details that lithography is a process of patterning. So suppose that uh, we have a we have a pattern. I will not get into like what this will look like and all. The real thing is much different. Okay. So suppose that on this we want to make such a pattern that these are electrodes, say gold, copper, or aluminum electrodes, and they will look like this. Okay, and another set of like say positive and negative electrodes, and they will look something like this. Okay, so we cannot directly make such things like I draw here. That cannot be done in case of when this dimension, say the gap is of 10 micrometer. This length is of say 50 micrometer. This thickness is of say 2 micrometer. Can we draw it? Yes, anyone who thinks can draw it. That is,
His
yes,
first process is bus connection process. I think that is a
which one?
lithography. Litho- Lithography process. First
Hmm.
step is uh, printing process or bus connection process.
Bus connection, I didn't get what you are saying about. Yeah, can you explain? Yeah, Karupu, can you explain what you are
Um,
talking about?
so PCB design first process is the bus connection or
Okay, yeah, a similar, like you are using the term maybe differently. Yes, if someone is familiar with PCB designing, lithography is used there also, but on a larger scale. That we draw the pattern using marker or say some enamel, and then like we etch out the rest area, and then that part is left, and then we remove it using acetone or other relevant material, and that pattern is left. So correct, that is lithography, like very like same thing like lithography. Lithography just uses that uh, in this case, since we cannot pattern using like physically we cannot pattern, so we use light as the patterning material. uh, it is when we talk about light lithography, we specifically call it as photolithography. Okay. Nowadays, there are more advanced lithography techniques like laser, UV, deep UV, X-ray lithography. Like a lot of techniques are gradually developing, and that is able to like if we talk about lithography, we are mostly talking about photolithography here, and photo means light, so light-based lithography. Specifically, we use 365 nanometer or 405 nanometer. That is the standard lithography wavelengths that are commonly used. Okay, but when if we want to go into nano and like very small uh, dimensions, then we go to deep UV, UV lithography, deep UV lithography, and these things. Okay, so lithography is a core process in which what we do is that we are able to make patterns. We will see how using light we are able to make small micro scale patterns. Okay, how that patterning is done. And this is a very important part of micro scale devices, like micro sensors. Then second thing is that like in macro scale devices, macro, what we do is that if we have to make something, ideally we can make a structure using any material, but we choose materials specifically. Say when we have to make a like a building, we choose cement and sand, gravel, and these things. But the same thing if we have to make a say a temporary housing, we choose wood, and if we have to make say phone casing, we will choose plastic and these things. So material selection here also is very important, like for what purpose we are going, so what kind of material will be used. So some common materials, like first very important and very commonly used material is silicon. Since this whole technique of microfabrication comes from semiconductor industries, so silicon by default becomes the primary choice. Okay, nowadays polymers are used, metals are used anyway to for contacts and this. That also some specific metals are preferred in this. So we will be discussing all these things in this in the next coming 3-4 weeks. Okay, so what is the application of this MEMS? So some of these are like, if you see in case of medical devices, blood pressure sensor, drug delivery system, like we saw how insulin is uh, being delivered with minimal pain, like it is much thinner than the tip is much thinner than a needle, and you will not even feel that some pricking has been done, no blood, nothing. Such systems are developed. If we talk about automobile industry, airbag deployment system, the like when some accident occurs, the mechanism that triggers the deployment of airbag, that is a MEMS based device that detects that some collision has occurred. That is ideally a very sensitive accelerometer. Like when the acceleration is too high, it will trigger the airbag deployment. That is a MEMS application. MEMS microphones are used, gyroscopes are used in our phones. So these are some common applications. So if you see this one, this is the image of a gyroscope of iPhone 4. So that is quite old one, but still you see the dimension is 500 micrometer this size. So the whole thing is actually encapsulated inside this. So this is not even that, it is inside that. Okay, so it is so tiny, and it like helps a lot while navigating and this. So this is also the image of a smartphone uh, gyroscope, which you see the patterns like this comb like patterns. When they move up and down due to the movement that we do, they change some resistance, they change some conductivity, and that's why they are able to generate some signals, and as such we are able to detect the change, like you are moving at what speed and all these things we are able to check. So we talked about good things of the MEMS, but there are some problems also associated with MEMS design. One is reliability under thermal and mechanical stress. Since it is a very tiny structure, heat and mechanical stress will have some effect. Many a times, it might be that nothing, like your phone, like fall 2-3 times, and after that, although physically looking it is perfectly fine, but some of its components are not working. Say accelerometer is not working, gyroscope is not working, camera might not be working. Like these are because these are very sensitive. Like although the external parts might not be that sensitive, but the internal MEMS structure and this chip, they are quite sensitive to mechanical stress. So they might get this comb-like structure. If it gets stuck, it is in micrometer. If it just gets stuck, your whole system is useless. This gyroscope is useless. So as well as if you treat this with too much of heat or too much of cold, in that case also they suffer some deformations. Okay, yield issue, that is that when you are making these devices on a single chip or something, it might be that you will not get the like if you are making 200 devices, you might be able to get only 100 or 120 devices working, not all. So yield is an issue because there are defects during fabrication. We will be seeing the fabrication steps. Then integrating with electronic circuits, because all the circuit cannot be built into a chip. So the chip, like these have to be made separately and then integrated together. That is a challenge. That is not very easy, but yes, this is possible. Like if we see about very big mechanical devices, the integration was like not possible, you can say, in many cases. But in this case, it is a tedious task. So these are some of the challenges. Like if you see, this is a surface of a MEMS device, and like not a MEMS device, a silicon wafer, and you see some film has been grown, and then there are some micro defects over it, and these defects will lead to degradation of the performance or failure of the devices that will be made in this region, this region, this region. Like if you see this, these are cantilever structures. Due to uh, change in temperature, they have like they have moved up because some expansion has occurred and they have moved up, and now they are of they are not working perfectly. They it might have be that if they are cooled and they might get corrected or may be permanently damaged, but in most of the cases such damages are almost permanent. So these are some of the challenges in MEMS design. So any questions still here? Anything to ask? Yes, anyone? Okay. So let's move to the next, that is future of MEMS. What we will expect in, like this is MEMS. We talked about this. So why we are talking about MEMS? If it is already there, what forward? Okay, what is the thing that will like that we will be able to do further? It is like there are some emerging fields like biomems and MEMS energy harvester, and nano electromechanical system, that is NEMS, advanced form of MEMS, you can say, where the dimensions are in nanometer. Many times when we are working in our, not many, most of the time, like when we are nowadays making sensors, we are actually dealing in nanoscales, like our film thickness and all, they are uh, in range of nanometer. Like we are depositing uh, some nanometer of material and then we are sensing it. And that like that is a very fascinating field, as well as it has a lot of scope, like lot of scope to make devices further miniaturized, integration of multiple devices in one, and these things. Then these MEMS devices are further scalable using advanced lithography techniques like UV, uh, extreme UV or deep UV. Okay, and as the AI and this AI and data science is growing, we will see MEMS system getting integrated with AI and smart MEMS system like sensors, and this will gradually evolve. So that is the future of MEMS, and that is the reason that we are discussing and focusing on this topic, like MEMS and microsensors. Yes. Any questions still here? We have completed summary of week one in a sense. We'll be discussing some questions based on week one. So any question, any doubt, any questions, or any input till here?
So flexible sensor like rubber based.
Just complete.
Sir,
I'm hearing.
I will message, sir.
Okay. Okay. Yeah. Any other questions? Anyone? Any questions? Any doubts? Yes. I will ask some people then. Hmm. Anbal Anbalangam. Yeah, Anbalangam M. Are you there? Hello. Vidhi Rawat or M. Kaushia. Yeah. Anyone? Please respond. You can unmute and respond. Not an issue. Okay. Flex or bend sensor. Yeah. Flexible sensors are a field. Like many many research is going on in flexible sensors. So it is, you can say, the major the difference is in the substrate. Here we are mostly using glass or silicon as the substrate when we are talking about MEMS generally. So when we replace this surface, the structure that we have to make, that is to be on a platform, that we call as substrate. In case of microfabrication, we are mostly calling it as a substrate. So that is the base material on which all our structures will be made, either deposited or cut out from it. Okay. So if we replace this substrate with some flexible materials, okay, like PET is one common flexible material, and there are other work like e-textile, and these things are also going on. So we call them as flexible sensors. So again, they are derived from uh, MEMS and NEMS only, but like researchers are working on replacing the uh, base substrate. Like in IIT Jodhpur, one group under Dr. Sri Prakash Tiwari, they are working on flexible sensors. So like we work together mostly. So we see that they use different materials. Like if you are interested, you can refer to their papers. You can just search on Google Scholar. They are making a lot of flexible sensors. Okay, like PET and paper-based sensors are also made. So paper is being used as substrate over it. So it is like certainly it has advantage as well as disadvantage, that it is much cheaper, environment friendly and all, but still not that robust to replace these sensors, that rigid sensors are there. So when we talk about flexible sensors, so it is flexible MEMS like that. Got my point? Fine. Okay. So now let's move to that part where all of you have to respond. Okay. What is the full form of MEMS? Yes, anyone? Yes, anyone like to answer, please? Unmute and speak, not an issue.
Micro electromechanical system, sir.
Micro electromechanical system, that is A. Any other answers to this? Anyone? Yeah, I think Sudhakaran, you said this, right?
So, micro
Okay,
electromechanical system is the same
yeah,
like first one. Sir. Mm.
first one. Okay, yeah. I don't have the option of giving you people 5 stars. Yeah, so we can just say good, right? So yeah, so first one, that is micro electromechanical systems, that is stands for. And why micro? Because we are dealing in micro scale mechanical and electrical components. Fine. So why is scaling important in MEMS? It increases weight, enhances the macroscopic effect, allows exploitation of microdominant forces, or reduces device functionality. Yes, anyone?
The third one allows exploration of micro domain
Dominant
force.
device forces. Yes. Any other answers to this? Anyone? There can be multiple answers which are correct. So feel free to answer multiple. These are like whatever questions I am putting, it might not be single answer. And like might not be that only one option is correct. Yes. Good. This one is good. Any other answers? Okay. So very correct that it is that we are able to exploit microdominant forces like higher surface to volume ratio, which in turn leads to higher surface tension, adhesion, and these factors. Okay. Now, in MEMS, what principle does a piezoresistive sensor use? Change in resistance due to stress, change in capacitance, light diffraction, magnetic field variation. Do you remember we talked about this piezoresistive something? Yes, anyone?
Change in resistance due to stress.
Good, good, very good. Yes, I think Sudhakaran was also trying to answer. Yeah, you can also answer.
So same answer. Change in
Same
resistance due
due
to
to stress. So, yes, good. So, yeah, Anbalangam, you are also saying something. You are not clearly visible. Audible, sorry. Yes, please speak. Hello, you are muted. Unmute and speak.
Option A, sir.
Option A. That is change in resistance due to stress. So, when we talk about piezo, that means something that responds to stress. Okay, so it is the change in resistance due to stress. And implying this, there are sensors that are called as piezoresistive sensors. There are some pressure sensors. There are some cantilevers are also some cantilevers also use piezoresistive material over them. There are pressure sensors which rely on this piezoresistivity, that when some pressure will come due to the stress, the resistance will change, and this in resistance will disturb the Wheatstone bridge kind of configuration, and you will be able to detect that difference, and that difference will lead to, like, you can calibrate it how much pressure is there. Which process is commonly used in MEMS fabrication? Injection molding, lithography, 3D printing, or casting? Yes,
Photography, sir.
lithography.
Sir,
Anyone else?
Lithography.
Lithography, good. But nowadays, this is the most dominant one, very correct. Nowadays, people are trying to use 3D printing also for this MEMS-based devices. So in future, you might be hearing or changing the answer to 3D printing. But at present, lithography is one of the most dominant. And 3D printing have this problem that its resolution is still around 400 micrometer. So it is a bit larger in like resolution compared to what we generally work when we are working in terms of MEMS devices. Like we might be going into 10 or 20 micrometers. So in that case, like this is for you can say the uh, in between, like when we are moving from macro to micro, the transition part at present we are able to do using some 3D printing techniques, but the resolution is still not that good. That's why lithography is still the primary process for creating microstructures. What is a typical size range for MEMS devices? Centimeter, millimeter, micron, or nanometers? Yes, anyone? This is the first thing we discussed. Yes, Aswin.
Micrometer.
I think
Micron.
nanometer.
Yeah. So don't get confused between the word microns and micrometer. They are same. Okay. Uh, like we cannot always say big names, so we put a short name to it. It is uh, micrometer or microns. Okay. So MEMS are the term itself is micro electromechanical system. So it is in micrometer range. Which force becomes dominant as the size of a device reduces? Gravity, surface tension, magnetic force, or electrostatic force? Yes,
Surface. Surface tension.
surface tension. Good. Any other answers to this?
Surface
Anyone?
tension.
Surface tension. Good. So, as the surface to volume ratio increases, surface forces like tension dominates gravity forces in microscale devices. What material is most commonly used in MEMS fabrication? Aluminum, silicon, copper, or gold?
Silicon.
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 Yes, very good. And why is it so? Anyone?
Because it is light-based material.
Yeah, I didn't get you. Because it is light.
Light-based materials, sir.
Okay. Any other explanations?
I think silicon is an pure semiconductor. Silicon and germanium.
Yes. Any other? See, the reason is like this is something that is there. Like the technology based on silicon is well matured compared to if we come up with a new thing. Like when we talk about flexible electronics or anything that has not yet reached till the point where silicon is still is there. To replace silicon at present, like it is quite like it will need a lot of money to replace silicon, we can say, because silicon uh, fabrication is very dominant, and it is like in almost all the devices you say it is silicon based. Now you might be some of you might be hearing that something called GAN charger are there, right? Anyone knows about GAN charger? Someone says that it's a GAN charger and it's smaller in size. Yes, anyone? When we are talking about this
Sir.
charging brick, yes. So that is again a semiconductor, just like silicon, although it is a compound semiconductor, but it has properties much better than silicon. But still, if you get deeply into it, you will see that this GAN is deposited over silicon substrate only. Because silicon, the technology is well developed, so we take silicon first and over it we deposit GAN. And that also we don't directly deposit GAN, we first deposit some other layers so that it will match perfectly and then GAN on the top. Okay, so the dominance of silicon is there because silicon is the technology related to silicon has matured well, and it is very dominant in semiconductor industry. That's why silicon is most commonly used. Although the starting we can say that it first started with germanium, but germanium had some issues like it was not very thermally stable and all. So people shifted to silicon, and this semiconductor industry grew to such a large extent that nowadays big names like Intel, Samsung, and TSMC, these are like big names in the world. They are all semiconductor fabrication working in silicon, right? That is why silicon has become dominant. And now silicon is the most common thing that we go for in case of semiconductor fabrication. Although you might see that silicon is having some issues like after 200 degrees it will degrade. The devices are not, we are not able to scale down the devices too much now because it has reached to some limit. Whereas the same thing, if we talk in terms of GAN and these things, the power capacity, everything is much enhanced, but still silicon is preferred. Reason being, silicon technology is too developed and too penetrated, like it cannot be replaced at once. Got it? That like there is no such reason that we are taking silicon only for this reason, but it is one of the most common one, commonly available, easily available to get a like I can give you a perspective that recently we were trying to get a GAN wafer that is grown on a silicon, small 2-inch wafer. So if we talk about, although it's not like silicon wafer, we are not fabricating, like not producing in India. So if we are importing, that 2-inch wafer will cost something around 1,000 to 1,200 rupees. But if you buy the same with a GAN layer on the top, properly grown GAN layer, it will cost you more than 50 to 60,000. So certainly the cost of your device will also increase that fold, like 500 to 600 times, or at least in this case 1000 to 50. So you can say 50-60 times. Okay, that is the reason that silicon is still preferred. If some other technology comes that is much robust and like cost effective, then people will switch to that. Yes, any questions still here? Main reason is compatibility with existing semiconductor processes. Yes. Any questions or anything you would like to add? Anyone? Okay. Can we move further?
Yes, sir.
Yeah. What is the primary limitation of MEMS device? High power consumption, difficult integration with CMOS circuits, limited reliability under extreme condition, or high manufacturing cost. Yes, anyone?
Sir,
Manufacturing cost high.
Yeah, let's speak one by one. Yes, Blessing, you were saying something.
sir, I
High
think
manufacturing
option
cost.
C,
Okay,
limited reliability under extreme conditions.
extreme conditions. Okay. Yeah, Anbalam,
Option
you were
D, high manufacturing cost.
high manufacturing cost. Okay. Yes, any other answers?
Sir, can I know what is CMOS circuit?
Uh, can you speak a bit louder?
Sir, can
Hello.
I know what is CMOS circuit?
Okay, CMOS.
Sir,
CMOS circuit, you can say the existing semiconductor circuits like transistors and these things. Transistor and chip like processors and all. Those are CMOS circuits. Yes, any other answers? So the problem with this MEMS devices mostly because they are actually made in silicon. Okay, they are not able to reliably work under extreme condition. Like I showed that they are susceptible to bending, they are susceptible to traps and all. The manufacturing cost someone was talking about that is taken care due to the semiconductor manufacturing. Anyway, we are already like manufacturing that, and we are able to manufacture at a very low cost. Nowadays, you can get small chip at 1, 2 rupees, 10 rupees, 20 rupees, like that. So cost is not an issue nowadays. It used to be issue when, like say, 20, 30 years back. But nowadays, uh, cost of these MEMS devices are not an issue much. But reliably working is an issue. Okay. Okay. Which equation best represents the transverse deflection of a cantilever? We talked about transverse and axial deflection of a cantilever. Yes. Anyone? Yeah. Anyone?
Sir, option B.
Option B. Right. What is the purpose of lithography in MEMS? Depositing materials on the wafer, remove unwanted parts of the material, pattern microscale features onto a substrate, or measure deflection in MEMS beams.
Sir, option C.
Option C, that is pattern microscale features onto a substrate. Yes, anyone else? Any other answer?
Option C, sir.
C, okay. So,
Option C,
C,
pattern microscale
pattern.
features
Yes,
on.
good. So, it's used to pattern, and patterning is the main part because anyone can like fill the whole substrate with anything, but patterning is an issue because no. Hello, am I audible? Just a minute. Hello. Yeah, can anyone respond whether I am audible or not? Hello,
Yes, sir.
Yes,
Audible.
sir. Yes, sir.
audible? Okay, fine. So, lithography defines patterns that guide subsequent etching or deposition steps in MEMS fabrication. That is, a feature like patterning the features onto substrate. In MEMS device, okay, this we have not covered, so we'll skip this. Which of the following can MEMS not directly measure? Pressure, acceleration, magnetic field, or temperature? Yes, anyone?
Magnet.
Magnetic field. MEMS sensor measure mechanical and thermal properties, but magnetic field and these things, since we saw that these factors are less, or like these forces are less effective in the micro scale. That is why we will need additional mechanism to detect magnetic field. Whereas temperature, acceleration, pressure, these can easily be detected since they are mechanical and thermal property. They depend, like they will define the mechanical and thermal properties. What does Castiglio theorem compute in MEMS? Voltage, stress distribution, deflection or force, or capacitance? Yes, anyone? We saw somewhere that when we were talking about AFM tape and cantilever, right?
I think C, sir.
See, deflection or force. So, have derived force from the strain energy stored in a structure. So, what energy due to the strain will be stored in the structure, that is computed using this theorem. Which MEMS application involves high sensitivity to motion? Pressure sensor, gyroscope, thermometer, or microfluidics? Sensitivity to
Sir,
motion. Yes,
gyroscope.
Ashwin. Yes, Ashwin, you are saying something. Yeah, anyone?
Sir, C, B, sir. B.
Gyroscope.
Gyroscope. Yeah, any other answers? So it's gyroscope that detect angular velocity for specifically important for motion sensitive applications like navigation, and they become even more relevant when humans are not navigating, but like autonomous devices are there, like you see nowadays autonomous cars which will navigate according to this only. They will not know that how much angle they have turned because we see things they don't see like this device. So gyroscope and these things will become even more relevant when we are moving towards such autonomous things, autonomous devices and all. Okay, why is strain energy significant in MEMS analysis? Why the energy that due to the strain in the MEMS is important? To determine the heat dissipation, to calculate deflections accurately, to optimize electrical resistance, to improve thermal stability. Yes, anyone?
Option B.
Option B. Okay. Yeah, any other answers? Yes, anyone?
So option T, sir.
D, to improve thermal stability. Yes. There is some energy, right? So this energy is related to deformation. That means like how much deformation will happen due to this strain, and that is essential to determine the deflection and stress in the MEMS structure. Fine. So I think Bleshan or who answered this B, right?
Yes, sir.
Yeah. So that is strain energy relates to deformation and is essential for analyzing deflection and stress in the MEMS structure. Although this same energy like accumulated over a period of time will also lead to heat dissipation and like uh, like that heat will come in terms of heat and all, but that is like when we are talking about the small structure, that is a different thing, but specifically this energy is significant for deflections. Okay, this I have put some more questions. Anyway, I will be putting this all in the slides. Like you will be able to access this by going to the course. Okay, in the course section you will see in the last there are live like live interactive sessions or something like that. From there you will be able to check the seat, all the slides, like this annotated, annotated both slides as well as this video link, everything will be available there. So any questions related to the topics we have, a topic we have covered in this lecture? Anyone? Yeah, please feel free to ask, have doubts. Like if you are not having doubts, there can be two things. One is that you have understood everything perfectly, or you are not understanding anything at all. Because if you are understanding something, there will certainly be some doubts. Yes, anyone? Okay, so next week topic is like coupled electromagnet mechanics, electrostatics, and Stickson in microsensors. Okay, that sir will also cover, and I'll be discussing the things here. So we'll be meeting again in the next session. So thank you all. Any questions, any query, you are free to ask. I'll be here for next 2-3 minutes. If you have any queries, you can unmute and speak up, not an issue. Yes, some question in the chat. Karupa, yeah, PPT. Yeah, I said no, that you'll get the PPT and everything in the course. Like if you open the course, you will see that at the bottom there a link will appear. You will be able to access all this. Even the recording I will be uploading on YouTube. And anyway, these recordings you can get on my YouTube channel, and there also I'll put a link for the slides. Fine. Yeah. Thank you all.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you, sir. Thank you so much, sir.